Hello and welcome back to Nunley Math. I am your host, Aaron Nunley. Thank you so much for joining us here again as we talk about special patterns when factoring. You will remember that we have already done factoring by removing a GCF, and then we did some factoring problems that could not be solved by removing the greatest common factor that we had to solve using guess and check. Now, this lesson is designed to give you another shortcut to make it so that you don't have to guess and check nearly as often. Guess and check is one of those methods that it's tedious, it's long, it's boring, but it is effective. But anytime we can find a pattern that allows us to not have to guess and check, we certainly want to make sure that we take full advantage of that. So here's what we're going to do. There's actually two patterns we're going to look at that are going to be very, very helpful to us. In order for us to talk about the first, what I'd like you to do is take just a second, pause the video, and I want you to try these 5 warm-up problems very, very quickly. Hopefully these problems look familiar to you from our polynomials unit when we talked about how we multiply binomials together. Once you've finished that, go ahead and restart the video. I'll talk you through each of these, make sure you understand what you're doing. If you find at any point that you are struggling with those, pause the video, watch me do 1 or 2, and then try the others on your own. Now, I'm going to assume that you have already taken your time to do that and you've already restarted the video and you're ready for me to explain. You'll remember we said that when we are multiplying binomials, we're going to take this first value in the first parentheses, the x, and we're going to multiply it by both the items in the second parentheses. So x times x is going to give me x squared. X times negative 3 is going to give me negative 3x. Then we're going to take this positive 3 times each item in the second parentheses, and we're going to get 3 times x is 3x, and we're going to get 3 times, remember this is negative 3, and that's going to give us a negative 9. So when I multiply those together, this is what I end up with. And then we notice something very important. Notice that the middle terms are opposites of one another. That's because what was in these parentheses was exactly the same, except one had a plus sign and one had a minus sign. That's going to cause these middle terms to become 0x. And so what I end up with is x squared minus 9. Now, when we learned this back in our polynomials unit, we said that if we can learn to recognize this, we can get from this step to this step without having to do this middle step. Just recognizing that the first number is going to be this value times itself, and the last number is going to be the 3 times itself. Or you could say 3 times negative 3 if you prefer, and that'll tell you where you get your minus sign from. Knowing that, when I get down to y plus 7 and y minus 7, instead of going to the trouble of doing this, I'm just going to look at this and recognize that this is the exact same item or exact same binomial, except that the signs are different. So rather than showing this middle step, I'm going to go through here and say, well, I know y times y is going to give me y squared, and I know 7 times negative 7 is going to give me negative 49. And so I can get this right away without having to bother writing out that minus 7y and plus 7y in the middle. I'm going to do the same thing here. M times m is going to be m squared. 10 times 10 is going to be 100. The signs are different, so I get m squared minus 100. Down here I have 2x times 2x, that's 4x squared. I have 1 times 1 is 1. 3x times 3x is 9x squared. 5 times negative 5, or negative 5 times 5 gives me the negative or minus 25, and you end up here. Now, the reason I make mention of this now is because we learned the difference of squares pattern. It says, if the numbers are the same but the signs are different, you're going to get a perfect square minus a perfect square. Today we're going to do that the other way around. In other words, if I can spot this difference of squares pattern, a perfect square minus a perfect square, I can write it in factored form without having to go to all the trouble of guessing and checking. Here's the things I'm going to look for. In order to be a difference of squares pattern, I have to have a binomial or 2 terms, and both the numbers in the 2 terms are supposed to be perfect squares. And there must be a sign between them. In fact, if I were you, I'd put a little star next to this, or circle this, or underline this, because this is a real trouble spot for students. So let's take a look and see. x squared minus 25. Is this a difference of squares pattern? Well, yes, it's a binomial. You have one term, two terms. X squared is a perfect square. It's x times itself. 25 is a perfect square. It's 5 times itself. So, yes, this is a difference of squares pattern. How about the second one? Notice this is a perfect square, x times x. 24 is not a perfect square. So this is not a difference of squares pattern. If at any point you want to pause the video and try these one at a time, I'd highly recommend you do that as well instead of just listening to me read them off to you. How about this third one? X squared is a perfect square, but negative 36 is not. This is not a difference of squares pattern. 4x squared is a perfect square. It's 2x times 2x minus, notice 15 is not a perfect square. This is not a difference of squares pattern. This one's a little tricky. Negative 49 is not a perfect square. Plus is a problem because there's supposed to be a minus sign. And 16a squared, this actually is a perfect square. Now, a lot of people are going to look at this and say, oh, well, there's a plus sign here, and this is not a perfect square. Therefore, this is not a difference of squares patterns. However, this one is. It's actually a little bit tricky, because if I were to rearrange this, and put the 16a squared first and the minus 49 second, notice this plus negative here? That's the same thing as subtraction. 16a squared minus 49. You might want to circle this one to make sure you come back to it. This is tough. This is tricky. Always make sure you're cautious. I knew this one would work because I have a positive plus this would be a negative. Notice this is a positive plus a negative, positive plus negative. If one of them's negative, it could still be a difference of squares pattern. The problem with letter C is the negative 36 and the negative x squared. They're both negatives. That's problematic. What about F? F, in fact, is a difference of squares pattern for the same reason E was. 9m squared plus negative 1, 9m squared minus 1. Notice 9m squared is 3m times 3m. 1 is 1 times 1. So how's that going to help us when we're factoring? Well, if I go to factor the binomial x squared minus 4, and I can look at this and recognize, wait a minute, this is a difference of squares pattern. Here's what I know. X squared is going to be x times x. 4 is going to be 2 times 2. Since there's a minus sign in the middle, I'm going to have one of each sign. See how that works out? This is a perfect square. This is a perfect square. So I'm just going to have the difference in the roots times the sum of the roots. Can you do this one on your own? I'm going to assume you paused the video and tried that. How does y plus 7 and y minus 7 sound? Notice it doesn't matter what order I put them in because multiplication is commutative. How about this one? Well, that's z minus 11 and z plus 11. Notice z times z gives you the z squared. 11 times negative 11 is that negative 121. If you were to do the middle terms, you would get 11z minus 11z. How about that one? That one actually is a difference of squares. Remember that m to the third times m to the third equals m to the sixth, because the rule is when you multiply like bases, you're going to add those exponents together. 16's root is 4, n squared's root is just n. I would suggest that if you're taking notes, you make a little note here to yourself that just says all even exponents. All even exponents are perfect squares. This is really hard to do with a mouse. Are perfect. I know because you guys are enjoying listening to me read that, right? Squares. There we go. That only took like half an hour to do, didn't it? Lengthened my video just a little bit. Yeah, all even exponents are going to give you perfect squares. Again, I'm recommending you pause these and try them on your own and then watch me do them. Notice 36x squared, this is 6x, this is 5y. Notice my little typo here, one of these should be a plus. I need to go back and fix that in my slideshow. If they were both minuses, the middle term would not go away. But if I change it to a plus, I get 30y and negative, or 30xy and negative 30xy. How about that one? Can you do that? Notice the square root of 9 is a 3. The square root of a to the 8th is a to the 4th, because a to the 4th times itself is a to the 8th. Square root of b to the 4th is b squared and b squared. Square root of 49 is 7. How about that one? 3a to the 5th minus 12, 3a to the 5th plus 12. How about that one? This one's actually a little tricky because a lot of people are going to say, well, yeah, this has a 7, this is x squared, this is 3, and this is x cubed. But let me help you remember that we always want to be looking for a greatest common factor first. Anytime we pull the greatest common factor out, it's going to help us make the problem a lot simpler. This one actually has a GCF of x to the 4th. Notice what's left over is a perfect square minus a perfect square. Your answer is 7 minus 3x, 7 plus 3x, but don't forget to include that x to the 4th out front. A little tricky. Again, put a little star next to that one. That's a tricky spot. People forget to take out GCFs all the time. Last one. Did you see the GCF in this one? 2a squared. Notice when I look at it, 18 and 50 don't look like perfect squares. But if I pull the GCF out first, what's left over is a set of perfect squares. How you feel about that? Again, this is something that is all about recognizing the patterns. Certainly we could go through and just guess and check our way through these, but if we can recognize this pattern right here and know what it turns into, we're going to save ourselves lots and lots of time and effort. Tell you what, here's a review for our second pattern. If I have x plus 5 squared, do you know what that would become? Hopefully you've taken some time and you've tried that on your own. A lot of people mistakenly call that x squared plus 25, which is not correct. Remember, x plus 5 squared means take the x plus 5 times itself, which means this is a multiplying binomials problem. There's my cursor. This is multiplication, which means I'm going to take the x times the x, I'm going to take the x times the 5, I'm going to take the 5 times the x, and I'm going to take the 5 times the 5. And I'm going to end up here. Notice that anytime what's in the parentheses matches exactly, the middle terms are going to be identical to one another. Notice x squared is x times itself, 25 is 5 times itself, and the two middle terms are the same. So I have a 5x and a 5x, or I have two groups of 5x's. This is x squared plus 10x plus 25. This is a pattern we talked about back in our multiplying polynomials unit as well. At the time we said it's useful and helpful as a shortcut, but it would be more useful later. This is actually the time when it's going to be extremely helpful to you, and it's going to save you a lot of time. What I'm going to do is each one of these, I'm going to go a little faster, and I'm going to leave out more and more steps. Okay? So I'd recommend pausing this and trying it on your own. I'm going to go ahead and do this. I know that the first term is going to be a perfect square. The first term is going to be a y squared over here. I know the last term is going to be a negative 7 times a negative 7. So I should have a 49 at the end. The other thing that I know is that the middle term is going to be a y times a 7 twice. Notice if we look over here at this example, I had to take the x times the 5, and then I had to take the 5 times the x. So when I do this a little faster, I'm just going to say perfect square, and then the middle is 2 times these two values, or 14y plus 49. Notice this time I do have the minus sign. That's because the two middle terms were actually negative 7y's, whereas over here they were both plus 5x's. How about this one? The first term I know is going to be 2x times 2x, or 4x squared. The last term is going to be 9 times 9, or 81. The middle term is going to be 2x times 9 twice. 2x times 9 is 18x twice, which is 36x. Again, this is a new slide for me, so it's got a little typo in it. This is 4x squared plus 36x plus 81. One more. 6x minus 4 squared. I know the first term is going to be 36x squared. I know the last term is going to be 16. The middle term should be 6x times 4, that's 24x's twice, or 48x. Couple things here. Notice when I'm doing this, I'm actually going to do this straight here. Some of you might need to show this step for a while. Some of you might even need to go back and do the long way for a few problems just to make sure you've got a handle on it before you try and do the shortcut. The trick here is to remember that we learned that anytime something is multiplied by itself, or a binomial is multiplied by itself, this pattern emerges. Notice if we switch it to a minus sign in the middle, the only difference is that now you've got a minus 2ab instead of a plus 2ab. I'm going to take those same rules and I'm going to use them backwards today. In other words, instead of multiplying things together to get the trinomial, I'm going to take the trinomial and figure out what was it that created the trinomial. There's a couple things you want to look for. First, the first and third term must be perfect squares. Notice x squared, 25, y squared, 49, 4x squared, 81, 36x squared, and 16. That's always got to be the pattern. Second, the second term, or this middle term, must be 2 times the roots. Notice the root of 36x squared was 6x. The root of 16 was 4. The middle is 2 times 6x times 4. So, if you think you've got that, I would recommend going ahead and trying to do this on your own. Just tell me if it's a trinomial square or not. If you feel uncomfortable, watch me do one or two and then try again on your own. Let's go ahead and do this first one. X squared is a perfect square. It's x. 16 is a perfect square. Its root is 4. If I double that, does it give me the middle? Yes, it does. This is a trinomial squares pattern. Y squared is a perfect square. 25 is a perfect square. That's y times 5 doubled. Is that 10? Yes, it is. Perfect square, not a perfect square. No, negative 49 is not a perfect square. This is not a trinomial squares pattern, and it cannot be factored using this method. 3m and 4, that's 12m doubled, is not 10. The middle should be 24m if this is a trinomial squares pattern. How about this one? A times 2 doubled. Is that negative 12? It is not. This is not a trinomial squares pattern. How about 4x? I'm going to write this down because it's getting a little complicated. 4x times 5y. Well, that's 20xy. Doubled makes 40xy. This does, in fact, work. Got the idea? All right. So here's what we're going to do. We're going to factor y squared minus 8y plus 16. And here's the way I'm going to do that. I'm going to look here and I'm going to say, okay, this is y squared. That is, in fact, a perfect square. It's y times y. I'm going to come over here and I'm going to look at this and I'm going to say, oh, 16 is a perfect square. It's 4 times 4. Y squared, 4 squared. The question is the middle 2 times the 4 times the y? Notice 2 times the roots. Well, that's 8y. It is. Therefore, this is a trinomial squares pattern, which means in factored form, this is y minus 4 times itself. I knew it was minus because this middle term had a negative. I also know that the signs must be the same in order for me to get a positive number here. Now, some people might prefer to write that as y minus 4 squared. There are times when each of those is going to be more useful than the other. Are you ready to try this on your own? If so, pause the video and keep going. I'm going to assume you've already done that. X squared is a perfect squared. 1 squared is a perfect squared. The question is the middle 2 times 1 times x? And it is. So this is x plus 1 squared, or x plus 1 squared. How about this one? Y is a perfect squared is a perfect squared. 625 is a perfect square. Is the middle 2 times the 25 times the y? It is. Therefore, this is y minus 25 times itself, or y minus 25 squared. How about that one? Did I catch you off guard with the GCF again? You gotta look for the GCF. Put a little star next to this one, reminding yourself to always look for the GCF. Taking out the GCF is the easiest way to factor. It's also the easiest thing to forget to factor. Once you pull out the GCF, you're going to ignore it for just a minute, and you're just going to factor this. Y squared is a perfect square. 49 is a perfect square. The question is the middle 2 times 7 times y? And it is. Notice this is y plus 7, y minus 7 times itself, and then don't forget to bring that 2 down. That is part of your answer. Some people prefer to write it this way. Again, I would suggest pausing the video and trying on your own. I'm just going to keep right on going. Don't forget to pull out the GCF. You're then going to ignore the GCF. Where'd my cursor go? There it is. And just deal with what's in the parentheses. X squared, 6 squared. Is the middle 2 times 6 times x? It is. That means this is x plus 6 times x plus 6. And once again, don't forget to bring your 3 down. There it is in a simplified form. How about this? 2x times itself, 3y times itself. Is the middle 2 times 3y times 2x? Why, yes, it is. There's your answer, or in a more simplified form. I do realize I'm going faster and faster as we do these. I'm going to suggest that you do pause and do these on your own. Y squared is a perfect square. 3x is a perfect square. Is the middle 2 times the 3x times the y? Yes, it is. And there it is in factored form. Some people ask me if I think it is important that we take this and rearrange it into standard form. Typically in standard form, the x's would come first and the y's would come last. It actually is going to work out the same either way. Your final answer would be 3x minus y times itself. There's a really cool explanation as to why that times itself and this times itself are the same thing. We don't really have time to get into that today, but hopefully we can pick that up somewhere else along the way. Last one of these. Did I trick you with the GCF again? Pull out the GCF first, then deal with the 4x squared plus 20x plus 25. 2x times itself, 5 times itself. Is the middle 2 times 2x times 5? Yes, it is. Don't forget to bring the 5 down. There's your answer. Or in a simplified form, it looks like this. All in all, this ought to save you a lot of time because otherwise you're going to have to go through and do some guessing and checking. So for example, if I were to go up here and do the first one, I could tell this was going to be y minus and y minus using our guess and check strategies. But remember, there's lots of things that could give us a 16. It could be 16 and 1, it could be 2 and 8, it could be 4 and 4. But if we learn how to recognize the pattern, we're always going to jump straight to the right one without having to guess and check all those wrong ones along the way. Now, a couple quick things real quick. We're always going to look for the GCF first. Look for the difference of squares pattern second. That's this pattern here. A plus b, a minus b equals a squared minus b squared. The third thing we're going to do is look for the trinomial squares pattern. which looks like this. And then when all else fails, we're only going to guess and check if we must. So when I look at this problem over here on the left and it says solve for x, I'm going to notice that this is not in factored form. So I'm going to ignore the equals 0 for a second. I'm just going to go through my process. Is there a GCF? There is not a GCF in this problem. Is it a difference of squares pattern, or is it a perfect square minus a perfect square? It is. This is 5x times itself. This is 6 times itself. As soon as I spot that difference of squares pattern, I know how to break this down. 5x squared, 6x squared becomes 5x plus 6 and 5x minus 6. And then we'll bring our 0 back down into the problem. Remember, the zero product property says in order for two things multiplied together to equal 0, either the first thing equals 0 or the second thing equals 0. And then we just solve those equations separately. Subtract 6 from both sides, divide both sides by 5, write it as a mixed number. Add 6 to both sides, divide both sides by 5, write it as a mixed number. And don't forget to circle or box your answer so that I know where your answer is. Over here on the right, let's do one more and we're going to call it a day. Does this have a GCF? It does not. Is it a difference of squares pattern? Well, I can tell right away it's not difference of squares because it's not a binomial. Is it a trinomial squares pattern? Well, is this a perfect square? Yes, it is. Is this a perfect square? Looks like I just gave away the ending there, didn't I? Yes, it is. So, wow, got one that didn't show up here. All right, this is my 3x times itself. This is the 8 times itself. The question is the middle 2 times the 8 times the 3x? And of course it was, otherwise that would have been a dead, there it is. There it would have been a dead giveaway. Don't forget your equals 0. Zero product property says that one of these must be a 0. However, if you look at them, they're both the same. Since they're both the same, I only need to solve it once. And I end up with negative 2 and 2/3. Which of course I'm going to circle or box. Now this is not really what we're talking about today, but I do want to show you something else that's kind of interesting about this kind of a problem. If I were to write this as a function, we put plus 64 equals f of x. And I were to ask you to find the zeros of the function. What I'd really be saying is if you were to graph this, what would this look like and where would y equal a 0? What's cool is y is going to equal a 0 at x negative 2 and 2/3. So I would go 1, 2, negative 3. Right about here is where this graph would cross the y-axis or the x-axis. Notice, by the way, since there's only one, it must be the vertex, which also gives us the line of symmetry. And wow, that's really bad, but you get the idea. So, wow, that's even worse. So this does connect back to our study of functions if you're interested in that as well. I believe that's all we've got for today. Thank you so much for taking the time to watch with us. I hope this is helpful to you. Again, factoring is something that gets better with practice. So take your time when you do these. Do lots of them. Ask lots of questions. Get lots of help. If you do those things, I promise you will get better. As always, thank you for joining us. You guys take care of yourselves. Best wishes to you all. Bye-bye.